Hello, this is video 83 and I'll be talking about the pendulum. The pendulum is another example of an object that undergoes simple harmonic motion. The pendulum is just a mass suspended from a pivot point by a light string or rod. So you can see there's a string, there's an object, that's a pendulum. It's going to oscillate back and forth. The reason that it oscillates back and forth is due to the gravitational force. You can see in this picture that the gravitational force points downward, but the tension points upward along the string, but the motion is this way. So you can see that the tension is not responsible for motion that is perpendicular to it. But what this picture shows is that the gravitational force has an x component here that is the force that is causing this motion. It's causing it to oscillate back and forth. So that's why we're calling it the restoring force. It's bringing the object back to that equilibrium position. And it turns out that this expression for this force, mg sine theta, depends on the displacement, as long as you're talking about very small angles here. And that means that it has the form of Hooke's law, and so it satisfies the criteria for the object to be undergoing simple harmonic motion, because the force depends on the displacement. Yes, it's an angular displacement, but it's still a displacement. So we have derived here the equation for the period of the pendulum. We're not going to derive it for you, but it comes from the previous equation that I just showed and having to do some calculus to get this answer. What we care about is just understanding this equation. So this tells us that the period of the pendulum, so how long it takes for a complete cycle, so it's oscillating back and forth, let's say this way and then this way, that's a complete cycle. The time for that depends on the length of the pendulum, and it depends on the acceleration due to gravity. I have noted here the period is independent of the amplitude. You might think that if you release your pendulum from all the way over here and it oscillates back here, that might change the period, but it doesn't. It's only the length and gravity, acceleration here, that affects it. If you have a bigger length, then can you see what happens to the period? It gets bigger, because this is in the numerator. The period gets bigger, that means it's more time. That means that it takes longer to oscillate when the length is bigger. And then when g is bigger, then it's actually going to take less time to oscillate. And you can think of that restoring force as just stronger when you have a bigger acceleration, and so it makes it oscillate faster. Let's do a question here. A ball on a massless rigid rod oscillates as a simple pendulum with a period of 2 seconds. If the ball is replaced with another ball having twice the mass, how is that going to affect the period? Well, we just saw that the period is equal to 2 pi times the square root of L over G. It does not depend on the mass, it does not depend on the amplitude, not on the mass, it doesn't appear in this equation, so the period is still going to be 2 seconds. Let's look at this example. It's a grandfather clock, that's a pendulum that has a period of 2 seconds if it's running properly, because it does one cycle in 1 second, half a cycle in 1 second, and then it continues the full cycle that takes 2 seconds to go back and forth. So find the length of this clock. How long does it have to be in order for it to take 2 seconds to do a complete cycle? So this is a plug and chug equation that does require a little bit of algebra. We have this equation for the period, and we want to get L by itself. So what we need to do is we need to divide by 2 pi to get square root of L over G, and then we need to square both sides to get rid of the square root sign. So t squared over 2 pi, all of that squared, that's equal to L over G. And then we multiply by G in order to get L by itself. So we're going to get G times t squared over 2 pi squared, which is equal to 4 pi squared because you have to square the 2 as well. And then we're going to plug in the numbers. This is t here to 2 seconds. G is 9.8. We're going to assume we're on the surface of the Earth because we're not told otherwise. So that means that when you plug in all these numbers, you're going to get 0.93 meters. So that's why these grandfather clocks are very big. You need a big length in order to be able to oscillate at that specific time. Let's do one more question to finish up this video. The mass on the pendulum of a grandfather clock can be moved up and down by means of a screw. A clock is running slow. Would you move the mass up or down to correct the error? So just visualize your pendulum here, and you can change the length of it. Now the period is dependent on the length as 2 pi square root of L over G. So if the clock is running slow, you want it to go faster. If you want it to oscillate faster, what do you want the period to be, bigger or smaller? To go faster, the period has to be smaller because the cycle has to take less time so that it's oscillating faster. So the period is smaller. That means that the length has to be smaller as well. So if your pendulum is like this, you want to make that length smaller. Can you see that you're going to move the mass up? Because now the length here is smaller than it was before. So that's it for the pendulum. All you have to really remember is that a pendulum undergoes simple harmonic motion, and be able to use the equation for the period, be able to solve for any of the variables.